Whoa, day 30 of quarantine. I've gone crazy. And my glasses broke. Like, seriously broke. All right. Well, let's get some practice in here on these t-tests. All right, so here we go. Sweet corn of a certain variety is known to produce individual ears of corn with a mean weight of 8 ounces. All right, pause! Remember, you want to stop and look at what you're dealing with, means or proportions, and clearly it name drops that we're dealing with means. All right. A farmer is testing a new fertilizer designed to produce larger ears of corn measured by their weight. He finds that 28 randomly selected ears of corn, so we have a sample size of 28, has a mean weight of 8.25 ounces. Since this is coming from a sample, that's your X bar. And the standard deviation coming from a sample is 0.8 ounces. There are no outliers in the data. That's going to be important because notice we don't have that central limit theorem. Central limit theorem wants to see at least 30 and we're only at 28. But by declaring that there's no outliers, that means we're okay, right? T distributions are robust. All right, moving on. Do these samples provide convincing evidence? So there's your clue, evidence. That means we are running a test, right? We're trying to find what the p-value is. That is your evidence. The cut score, right, your significance level is alpha 05. So if our sample has less than a 5% chance of happening, that means we've found significance. All right, so here we go. First, we define what this problem's all about. It's about means. So it's the true mean weight of corn. I think technically sweet corn, but whatever. The null hypothesis. All right, so what usually happens? What usually happens is we have a weight of 8 ounces. But this farmer is trying to make this corn bigger. So we're looking for evidence that it's more than 8, right? So did this fertilizer increase the weight? They want the alpha to be 05. All right, so the next thing to do is check conditions. Conditions. Number 1. Random. It says that he finds a 28 randomly selected. There you go. So it is random. Random stated. All right. The next thing is that normal check. The problem does not say, "Hi, I'm normal." Okay, so that doesn't work. The problem does not have at least 30, so central limit theorem does not work. But since they say there are no outliers, okay. T distributions, which is what we're working on, has more area out in the tails. So it's okay if it's not perfectly symmetric, as long as there's no outliers in the data. So normal, let's see, no outliers, safe to proceed. All right, and then the third one is independence. We want to make sure that we're not sampling too many ears of corns. So for independence, let me shorthand it there, we're going to have to assume at least 10 times n, so 280. Assume at least 280 ears of corn in population. Pretty sure you'd have a lot more than that. I'm not a corn farmer, right? I can't even take care of my own hair. So anywho, formula time. Alrighty, this is a t-test, right? It's a t-test because we're working off of a sample standard deviation. All right, so we're finding where we are on the t-curve. How far away from the middle are we? Okay, so this is where we take our sample. So our sample is 8.25 ounces. That's what this new corn is turning into. We want to see how far away that is from what we usually expect, which was the 8, divided by how many standard deviations that is, so 0.8. But we have to adjust it based on stats, diet, trademark. All right. Then we have degrees of freedom, which is based on your sample size minus 1, so 28 minus 1. We are on the 27th t-curve, right? Remember, there's many different t-curves. We are on the 27th t-curve. All right, so at this point, I usually stop writing and I go to T.I. Joe. Head on over to Step World Tests, and you're going to scroll to number 2, t-tests. We have the stats. I don't have the raw data. All right, so on the stats, the claim is that corn weighs 8 ounces. Our sample was 8.25 ounces. The sample standard deviation is 0.8 ounces. We had a sample size of 28 ears of corn, and we're looking for evidence that it got larger. So we want the symbol to match the symbol that's on the paper. So notice it's going that way, that way. All right, calculate. We are at 1.65. All right, so that is our test statistic, aka t-score, z-score, right? So we are at 1.65. So if you sketch out a little curve real quick, 0 is in the middle, and you've got 1, 2, 3 standard deviations to the right, 1, 2, 3 standard deviations to the left, and we're sitting here at 1.645. So 1.6, it's like right here. All right, so this area under the curve that I just shaded in pink, that's your p-value. So back to T.I. Joe, my p-value is 0.548 and some change. So p-value, area under the curve, is 0.055 if I round that up. All right, so do we have the evidence? Time to compare our p-value to the alpha. Our p-value is 0.55. Is that smaller than the alpha that we started with in the beginning, 0.5? And no, it's not. It's really close, but it's got to be smaller than, and it's not quite. So we don't have the evidence. I'm going to put a little strike through, right? It's not less than. So we failed to reject, barely. All right, we failed to reject the null hypothesis. So as far as we can tell, this fertilizer really didn't help. All right, the sample that we got, 8.25, could have just happened by chance. Nothing special with the fertilizer. But that doesn't mean all is over. That farmer needs to keep trying, keep taking samples, adjusting the formula till they find something that works. All right, so concluding sentence. I've got barely enough room. I'll fit it right here. I'll do it in pink so that it doesn't blend. We have insufficient evidence, not enough. We have insufficient evidence at alpha equals 0.05 to conclude. All right, and we want to make our conclusions in terms of the alternative hypothesis. So the alternative was we're looking for evidence that the weight had increased from 8 ounces. All right, you can also steal the language up here, evidence that the fertilizer had a positive impact. So we have insufficient evidence at alpha equals 0.05 to conclude the fertilizer had a positive influence. And I'm out of space. So there you go. All right, so define what it is we're investigating. What's the claim and what are we looking for evidence of? State that cut score, right, your significance level. Check those conditions, make sure everything's okay. Formula, right, we want to find out where we are on the curve. P-value, how much area is under that curve. So that's the probability of this sample happening. All right, so a 0.055 chance, so like a 6% chance. Low, but not low enough. So we have insufficient evidence to conclude that this fertilizer worked. All right, okay, so let's check out number 2. The developer of a new filter for filter-tipped cigarettes claims that it leaves less nicotine in the smoke than does the current filter. Because cigarette brands differ in a number of ways, he tests each filter on one cigarette of each of the 9 brands below and records the difference in nicotine content. His results are given in the table below. Do the differences in the paired data adequately meet normality condition for a T procedure? Okay, so they're asking us to take the difference. All right, so old minus new. All right, you can do it by hand. You can have T.I. Joe do the difference. I don't know. I think I will pause the video real quick and type it in to save some time. So get your calculator, start typing, and we'll meet up. I went to Stat World, Edit, Clear, and I typed in the old filter and the new filter, and then I highlighted L3, and that's where I'm going to do this difference here. It doesn't matter which way you go. All right, they didn't say which way to go, so I just went with the first and then the second. So I'm going to take list 1, so second number 1, minus list 2. Whoop. There we go. All right, so to look for normality, we clearly don't have 30 samples. 1, 2, 3, 4, 5, 6, 7, 8, 9. We only have 9. So we have to look at a picture of our data here to see if it is, you know, following a symmetric shape. Make sure there's no outliers or gaps in our data. So I'm going to head to second y equals to take a look at what's happening. So plot 1, it's a histogram that we want to do. The difference I put in list 3. All right, so I want list 3 to be graphed here. So list 3. When you're ready, you hit zoom 9. It's so fine, it's a friend of mine. Zoom 9. What is that? Oh, you know, I probably have something in my y equals from my algebra class. Let's see. It's thinking about life. Well, it's still graphing, but if you just focus on that histogram, you'll notice it's not quite perfectly normal, right? We've got a little bit of a skew going on. However, there's no gaps. I don't have a piece that's way over here all alone, right? An outlier. So it's safe to proceed. And that's only for these t procedures here. So we are safe to proceed with the t distribution because there's no gaps or outliers. Okay, so what you would have to do on a free response is sketch down what you're seeing in your graph. Yeah, I had some stuff in there. Oh my, bark, bark. All right, so you want to sketch down your graph and talk about how there's no gaps or outliers in there. All right, so there's one more problem to do. Honestly, let's hold off. Let's do this problem on Wednesday. So enjoy your Tuesday. Hope you're doing okay.